All right, guys. At this stage, you've either watched one or two videos on the foundations of hypothesis testing, again, STAT1800. Um, what we want to do, or I don't know about what we want to do, what we're going to do is we're going to dive into just hypothesis testing for a population mean. So let's do it. When we think about a hypothesis test for a mean, it all relies on I should say the type of test that we use depends on what we know about the population's standard deviation. For example, if the population's standard deviation is known, which is really, really rare if it is, but in cases where it's known, we use a z-test. And if the population standard deviation is unknown, we use a t-test. This is it aligns perfectly with constructing confidence intervals for mu. When the population standard deviation was known, we used a z-interval. And when the population standard deviation was unknown, we used a t-interval. So, sharing a lot of the same principles. So, first of all, let's look at a z-test if the population standard deviation is known. So, again, the first thing you do is as we said in the previous video, you state your null and your alternative hypothesis, you set your level of alpha, and you get your sample size. But the next thing you would do is you would calculate your test statistic. Now, if we have a situation where the population standard deviation is known, then we use our test statistic is called a z-statistic. So the author here in this PowerPoint has that listed as Z and then subscript STAT. Well, the way you calculate that is you take the sample mean minus mu. And guys, mu is the value that is hypothesized in the null hypothesis divided by the standard error. Now, I think there needs to be parentheses put around the stuff in the numerator and the stuff in the denominator. But I'll do some illustration videos coming up, and I'll make sure that I do that. So we're going to look first of all at a critical value approach after getting the test statistic, and then we'll look also at a p-value. So for a two-tailed test, the mean, sigma known, convert the sample statistic to our z-stat, like we talked about on the previous screen. Determine the critical values for z based on our specific level of alpha, usually 0.05 using StatCrunch. And our decision rule, if our test statistic falls in the rejection region, we reject H sub O, otherwise we fail to reject H sub O. So two-tailed test, there are two cutoff values, two critical values defining two regions of rejection. I call the blue area to the right the upper tail of rejection. That's cut off by the upper critical value. And if we concentrate on the lower blue shaded area, that's the lower region of rejection, which is cut off by the lower critical value. Anything between those, we fail to reject or do not reject the null hypothesis. Guys, 6 steps in hypothesis testing. State the null and state the alternative. Second thing, choose your level of significance. Guys, alpha will almost always be 0.05. Choose your sample size and determine the appropriate test statistic and sampling distribution. If we're conducting a test of hypothesis for a population mean, our sampling distribution is either going to be the Z distribution, and that's if our population standard deviation is known, or the T distribution if the population standard deviation isn't known. So if we do a z-test, we're using the Z sampling distribution, mean 0, standard deviation 1. If the population standard, or if we're using a t-test, then we're using a t distribution, which is a function of the degrees of freedom. So part 3, step 3, determine the critical values to divide the two regions. Collect your data, compute the value of the test statistic, see where it falls, make a decision. If the test statistics falls in the non-rejection region, then you fail to reject the null. If it falls in the rejection region, you reject the null. All right, here's going back to the manufactured bolt, which we saying has a should have a mean diameter on average, mean diameter of 30 millimeter. Now we're assuming that the population standard deviation is 0.8. So guys, first thing we do is state the appropriate null and alternative hypothesis. H sub O is mu equal 30. H sub 1 or H sub A is mu not equal to 30. This is a two-tailed test. How do you know that? Anytime you have not equal to in your alternative hypothesis, you have a two-tailed test because you have two tails of rejection region. Number 2, specify the desired level of significance and sample size. Again, I've told you alpha is almost always 0.05, and they have decided to sample 100 bolts. Since the population standard deviation is known, this is a z-test, so we'll use the z-distribution. Again, mean 0, standard deviation 1. Determine the critical values. Guys, I'll show you how to do that in a future video, but for alpha equal 0.05, the critical z values are plus or minus 1.96. Now, you probably remember that 1.96 plus or minus 1.96 was the z critical value for the 95% confidence interval. Do you think there's any relationship between the 95 and the 0.05 adding up to 1? Absolutely there is. So let's just file that under more to be taught later. All right. Number 5, collect the data. So let's say that let's just assume that the sample results, that the X bar was 29.84. We sampled 100 of them. And again, the population standard deviation is 0.8. So what they've done is they've calculated the test statistic for you. They've inputted the inserted the 29.84 in for X bar, the 30 in for mu, the 0.8 in for sigma, and the square root of 100 as the square root of n. They've calculated the numerator, they've calculated the denominator separately, and they come out with a test statistic of negative 2.0. This tells us that our sample data is 2 standard errors below the value that is hypothesized in the null hypothesis. In this case, 30. So is the test statistic in the rejection region? Well, you can see the rejection region is defined by negative 1.96 and positive 1.96. So the negative 2 falls to the left of the negative 1.96, so it's in the rejection region. So finally, what we do, we reach a decision. Since our test statistic falls in the rejection region, there is sufficient evidence that the mean diameter of the manufactured bolt is not equal to 30. P-value approach. Let's do the same problem using the p-value approach. Now, guys, I'll tell you, the p-value approach is much, much, much easier, I think, because you don't have to really calculate anything. You'll plug your information into StatCrunch. It will give you a p-value. You compare it to your alpha, make your decision. So the p-value approach will be the one that I'll depend on most in teaching you hypothesis testing in the future. But anyway, it's customary to teach both the critical value approach and the p-value approach when teaching business statistics. In fact, the state of Ohio requires this. It requires that we do that. So guys, the p-value is a probability of obtaining a test statistic equal to or more extreme than the observed sample value given that H sub O is true. So given H sub O is true just says that we have this sampling distribution that's centered around the value that's hypothesized to be true in the null hypothesis H sub O. So, guys, the p-value is called the observed level of significance, and I really wish that second bullet wasn't there because I think that gets confusing for students. So anyway, the p-value is the observed level of significance of your sample data. Approach to testing, we calculate our p-value, compare it with alpha. Well, that was loud. If our p-value is less than alpha, we reject H sub O. If our p-value is greater than or equal to alpha, we fail to reject H sub O. All right, so a little slogan there. If the p-value is low, then H sub O must go. I've never heard that before. 5 steps instead of 6 steps for the p-value approach to hypothesis testing. Again, state H sub O and H sub A or H sub 1. Choose your level of significance, alpha, and sample size. Collect your data. Determine the appropriate test statistic and sampling distribution. Collect your data, compute the test statistic and the p-value, and make your decision. Here's an example. Same thing. The bolt problem. Supposed to be 30 millimeters. Population standard deviation is given at 0.8. So we choose 100 randomly selected bolts. Again, population standard deviation is assumed to be known, so it's a z-test. Calculate your test statistic. It's still -2. The test statistic doesn't change. It's the same value. It's calculated the same way. Has the same notation, z subscript stat. Whether you're doing the critical value approach or the p-value approach. Test statistic is calculated the same way. Calculate the p-value. So the p-value is the area to the left of -2 and to the right of +2. So guys, that's a little bit confusing. If your test statistic turns out to be -0.4, then you look to the left of -0.4 and to the right of +0.4, because at random it's equally likely that it falls in either tail, it being our sample data. Best thing to do is if your z critical, your a test statistic in this case is -2, calculate the area to the left. Calculate the area in the tail. If it's +2, calculate the area to the right. So if your test statistic is positive, calculate the area to the right. If your test statistic is negative, calculate the area to the left and multiply by 2. That always gets you the right p-value if you're conducting a two-tailed test. Is the p-value less than alpha? So our p-value is 0.0456. It's less than 0.05, so we reject the null hypothesis, just as we did with the z-critical approach. So the connection between two-tailed test. A lot of people say, well, why do I even need to conduct a test of hypothesis when a confidence interval does the trick for me? And it really does, because if you look at the 29.84 and construct a 95% confidence interval around it, you can see that the hypothesized value of 30 is not contained in that interval. So therefore, since there's a 0.95 probability, that interval contains the mean diameter of all bolts produced by this manufacturing system, you would reject at 0.05. So if we constructed a 99% confidence interval and the hypothesized value doesn't fall between the two values, then we reject at the alpha equal 0.01 level. If we do a 90% confidence interval and it's not, the value in H sub O isn't contained in the interval, again, what's 90 minus 100 minus 90? It's 0.10, right? So we would reject at the alpha equal 0.10 level. All right, more about that in the future. So guys, do you ever truly know sigma? Probably not. I don't think there's many real-world business solutions where sigma will be known. Some people say, well, if you know sigma, you must know mu, so why make hypothesize about mu? I don't truly believe that. I think there are places where we could know sigma and not know mu. I think I used an example in a previous video. I know the population standard deviation for IQs is 15, but I don't know the average IQ for all nurses in Ohio, mu. So I think there are some cases where sigma could be known, but population mean isn't known. But guys, most cases that I run into in the research that I do and the advising I do for my PhD students and my master's level students, we don't rarely, in fact never, have we run into a situation where sigma is known. So that brings us to the next test. What do we do when we have a population or a hypothesis test for mu and sigma isn't known? Well, if the population standard deviation isn't known, you're going to use the next logical choice, which is the sample standard deviation. Because you've changed the dynamics of the z distribution, because the z distribution assumes that sigma is known, then you have to use a different distribution which doesn't assume that sigma is known. It's called the t distribution. So guys, when using the t distribution, you assume that the population you are sampling from follows a normal distribution. That's an important assumption. And if it doesn't follow a normal distribution, then you need your sample size to be relatively large. And we typically say relatively large is 25 or 30. Usually ensures that your sampling distribution will be normally distributed. And so all of the steps and concepts are the same. So that's the good news. So guys, the test statistic is calculated the same way, except first of all, you can see the notation is T sub stat instead of Z sub stat. So the T test uses T sub stat, the Z test uses Z sub stat. And you can see in calculating the test statistic, the only difference is instead of having sigma, we have S divided by square root of n instead of sigma divided by square root of n. So an example, average cost of a hotel room in New York City is said to be $168. I think that seems a little low to me. I've only been there once, so I'm certainly not an expert. But anyway, to test it, it looks like they've taken a random sample of 25 hotels. And it looks like the X bar, the bar is kind of off, so it looks like the sample mean is 172.5 and a standard deviation, a sample standard deviation of 15.4. Now guys, look down at the bottom, you can see the fine print. Assume the population distribution is normal. Now we got a sample size of 25 or more, 25. So we could probably go ahead and conduct this even if we didn't know the population distribution was normal, just because our sample size is 25 or larger. So guys, the null hypothesis is H sub O colon mu equal 168. The alternative hypothesis, H sub 1 again, or H sub A, is colon mu not equal to 168. Two-tailed t-test. First of all, alpha 0.05, degrees of freedom are 1 minus our sample size, which is 24. We find the t critical values just like we did back when we were doing a 95% confidence interval in a t interval. We calculate our test statistic. You can see that its value there in blue is 1.46, telling me that the sample data lies 1.46 standard errors above the claim in the null hypothesis. The mu is equal to 168. Okay? So guys, since that falls in our do not reject region, we would fail to reject, and we conclude that there's insufficient evidence that the true mean hotel cost in New York City differs from 168. Guys, again, there's depending on the textbook, there's a lot of variation on that. Some textbooks say a sample size greater than 30, some say greater than 25. As long as your population is not severely skewed, you can use the t-distribution. And there are different ways to evaluate whether the normality assumption has been satisfied. We can look at histograms, box plots, and there's something even called a normal probability plot that I'll teach you a little later. So same thing, connection to from t-test to t-intervals. You can see that this interval does contain the hypothesized value of 168. So that leads us again to not reject the null hypothesis. Now, guys, another thing you tattooed the brain, this consistency between the results of a hypothesis test and the confidence intervals only holds true if you're doing a two-tailed test. If you do a one-tailed test, you can get into some wacky results where your test of hypothesis actually rejects the claim in H sub O, but your value is contained in the interval. So we'll talk about that in a later video as well. So this correspondence between the consistency of the information provided in terms of rejecting or fail to reject the null based on the confidence interval and the test of hypothesis is only true if you have a two-tailed test. All right, speaking of one-tailed test, what happens if there's reason for us to focus on a particular direction? Well, you can see where when you do a one-tailed test, this is a situation where there's the goals of your study want to focus on whether a value is actually higher or lower. So a situation that may be applicable is, let's say that you're working at a grocery store, a grocery market, and you're currently selling, so much of a particular item. And you go in and you implement a particular marketing strategy, and you're hoping that that marketing strategy increases the sales. So you might want to conduct a one-tailed test in this situation to see if it's actually increased the gross sales. So notice that the alternative, notice that the null hypothesis changes. The lower tail test, which is less than, is the first illustration, and the upper tail test, which is greater than, is the second illustration. So if I wanted to see if this marketing strategy had increased sales, I would use the upper tail test because I'm focusing on increasing. So again, make sure you get those in your notes. So it wants to illustrate a lower tail test. So maybe an example of something that may happen here in a lower tail test is, let's say you have a particular a company, and you do something that's going to reduce some sort of expenses. Maybe you come up with a new route for your salespeople that's going to decrease the average number of miles driven each week by the fleet of cars. So that might be a situation where you do a lower tail test where you are implementing some sort of procedure where you actually want something in your company to decrease. And typically something that's associated with any sort of expense, if you can implement something that decreases, you look really brilliant, which is cool. Upper tail test, I just told you about an example of it. So all of the rejection region is in the left tail. Let me go back here. In a lower tail test, all of the rejection region is in the left tail. In a upper tail test, all of the rejection region is in the upper tail. Again, let me go back again. The purpose of this would to show that something has decreased. The purpose of the upper tail test is to show that something has increased. Okay? An upper tail and lower tail test have only one critical value. So all of our rejection region, all of our alpha is put in one tail. it's not split and put into two tails as it is in a two-tailed test. All right, let's get into an example. A phone industry manager thinks that customer monthly cell phone bills have increased and now average over $52 a month. So the company wishes to test this, and they are assuming a normal population. Now, by assuming a normal population, it just says you can work with a lower sample size. If you don't have that, you have the assumption of a normal population, then you need to focus on 30 or higher. So the hypothesis test, the null hypothesis is the mean is not over 52. And the alternative hypothesis is that the mean is over 52. So this time, let's say that alpha is 0.10. Now guys, usually alpha isn't 0.10. Usually it's set at 0.05, but that's fine, 0.10. And if alpha is 0.10, then we find our rejection region based on that. So it turns out that our critical value is 1.38 for degrees of freedom 24. So any test statistic above 1.318 is going to reject the null. Any test statistic below 1.318 is going to do not reject the null, fail to reject the null. So inquiring minds would want to compute the test statistic. Well, you can see that they've done that. They calculated a t sub stat, just as you would expect that they would, by inputting the numbers into the proper places. Sample means 53.1, so they put that in for x bar. The hypothesized value is 52, so they put that in for mu. The sample standard deviation is 10, so they put that in for s, and sample size 25, so they put that in for n. So the 0.55 falls to the left of the 1.38, so we fail to reject and find there is not sufficient evidence that the mean bill is over 52. P-value, same thing. What we do is we find our test statistic. In this case, it's 0.55. If we're doing a right-tail test, we find the area above 0.55. If we were doing a left-tail test, we would do the area to the left of our test statistic of 0.55. Well, this is easily done in Excel or StatCrunch, as we use in our class. We would find that the p-value would be 0.2937. It's greater than 0.10, so it leads us to the same decision of failing to reject the null because our p-value is higher than our set alpha of 0.10. Well, guys, that's all I got for you. We'll get into a preview of hypothesis testing for population proportions yet, and then we'll start working problems. We'll put all this stuff to test. So take care.